Yes, okay. Welcome everybody to the International Seminar on Automorphic Forms. Today we have Zhiyuan Li that will teach us about the theta series and tautological cycles on orthogonal Shimura varieties. So please.
Okay. Thanks very much for the invitation. It's my great pleasure to speak in this seminar. So today I'm going to talk about the theta series and some cycle theory on Shimura varieties. And because I'm actually an algebra geometer, so I will spend some time on the geometric background of this work. And this work is actually joined with Manuel and Zelin Ye and also Chen Xinhuang. The other two Chinese guys are my students. Okay, let me start about the motivation. So the motivation is coming from the cycle theory on modular spaces. So let's just briefly recall, because this is, at least for me, this is quite motivated. So let MG be the modular space of smooth curves, or equivalently, the modular space of compact Riemann surfaces of genus G larger or equal than 2. And it's well known that this modular space MG is a quotient of the Tecumseh space by its mapping class group. So it's kind of a quotient space. And it's actually an analytic variety of dimension 3G minus 3, okay? And people know, it's well known that it's actually an algebraic variety because by the work of the Lee-Mumford, there is a projective compactification of MG called the Lee-Mumford compactification. So it's denoted by MG bar. And this compactification is obtained by adding several irreducible components. Okay, so its boundary is called dimension 1, and it actually has G divided by 2, take the lower bracket, round down of the G over 2 plus 1 irreducible component. For each irreducible component, basically, it parameterizes some nodal curves or stable curves. Okay. So this is this description of the generic point of this boundary component is described in this equation. Like for delta I, it parameterizes reducible curves, and the component, one of the component has genus I, the other has G minus I. Okay, so this is the well-known picture. And I'm going to talk about the intersection theory of this modular space, and largely motivated from the super calculus. Okay, so this is the intersection theory on Grassmannian. So different from the case of supercalculus, because in supercalculus you are talking about the intersection theory on a homogeneous variety. So the Chow group comparable, easy. But for MG, the Chow ring is actually highly complicated, because even it's probably people believe that for large G, this actually is not finally generated. Okay, so it's infinitely generated. But however, even we have very, very complicated ring, but Mumford gave a so-called tautological ring, which is a subring inside this Chow ring, and he believes that this captures its most or essential part of this modular space, the cycle theory of this modular space. Let me just briefly recall his construction. So remember, a good thing for modular space is it carries natural object. Okay, so for modular space of curves, because it parameterizes all the smooth curves of genus G, so we can take it as a universal family. That means it has a family of smooth curves of genus G, and for each point C, and its fiber is itself. Okay, so this is the universal family. Usually we will denote this universal family by MG1, because this parameterizes the modular space of genus G with one marked point. Okay, as the mark point is varying, and this recovers the curve on the fiber. Okay, so usually this is a standard notation to denote this universal family. So once you have this family, and then we can take the relative tension bundle. Okay. I have to admit there is a little, there's some subtlety of the story here, because if you take the universal family, usually you have to work with the stacks. So in this talk, I will try to not distinguish the difference between cost-module space and the stacks. Okay. So we just pretend everything is kind of a fine moduli, and we do have some nice universal family. Okay. Otherwise, you just you need to take some level structure. Okay. And suppose we have such a universal family, and then we will have this relative tension bundle. Okay. And then here's the Mumford's kappa class. So given an integer I, we can consider the first chunk class of this relative tension bundle and do the self-intersection I plus 1 times. Okay. And once you do the self-intersection, you get an element on the choke group of the universal family, and then you push forward to the base. Okay. You use the push forward of pi and map the self-intersection to Mg. And then you get a cycle of codimension I. Because it is map, the fiber is a flat family of curves, so the fiber has dimension 1. Okay. And then Mumford defined the subring, generated by these kappa classes called the tautological ring. Okay. And the Mumford slogan is basically that this tautological ring encodes the essential, the important geometric data on the Mg. Yeah. So from construction, you can see that first, this kappa class actually defined naturally carries the canonical geometrical cycles on the fibers of the curves, because on curves, the most canonical cycles is this relative tension bundle, which is a divisor class, okay, on the fiber. And this tautological ring is clearly finite generated because we only have finite many kappa classes. Okay, so this is nice. Because for the entire Cho ring, is probably infinitely generated, but for this ring, it's finitely generated from the definition. So in last decades, actually, like 30 or 40 years, people have spending a lot of time to studying this tautological ring, and there are some structure of the tautological ring we can say about this on this ring. Due to a lot of people, for example, Hara, Luyanga, Faber, and actually I can put a lot of names if you extend this story to not just MG, but to MG bar, MGN bar. Yeah. But for MG, I will focus on MG the case. There are 3 important results. The first one I called Mumford's conjecture. So Mumford conjectured that for the tautological ring, first is a graded ring. Okay, if we look at its codimension 1 piece, it occupies the entire Picard group, and so that means the Picard group is 1-dimensional. Its rank is 1. Okay, so generated by kappa 1. So this is the first result, and if you look at the entire ring, it's generated not for all the kappa classes. It's only use a third of them. Okay, from 1 to G/3. Okay, so not all the kappa classes. And the second one is we have the vanishing. So if the codimension larger than G-2, this graded piece actually is 0. So we have the vanishing. And when the codimension is exactly G-2, it's 1-dimensional. So we call it 1-dimensionality. Okay, so this is pretty simple. Okay, from the construction, and this is now a beautiful theorem for the cycle theory for MG. Here is some remark. The properties 1 to 2 is actually part of Farber's conjecture. So Farber has made a conjecture on the structure of this ring, not for the generators, not only for generators, but also for the relations between them. So actually Farber's conjecture includes so-called Gorstan property that means the intersection pairing, okay, from RD to RG minus 2 minus D is perfect. Okay. So remember that MG is non-compact. So the traditional Poincare product is not perfect. There is no, for higher dimensional is 0. For top dimensional is of course 0, is non-compact. But we have a one-dimensional thing, which happens when D equals to G minus 2, and it's natural to ask whether this pairing is perfect. If it's perfect, then that will be nice. And this property has been verified when G less than 22. Yeah, so that's the way why Farber made this conjecture. But nowadays, people think this probably not true when G gets larger. So I didn't mention too much about this conjecture, but remember, this is also some long-standing question on MG. Okay, for MG bar, there are some analogous results, and actually Mumford and Farber, they have similar constructions of the tautological ring. And for the coordination 1, this is actually the entire Picard of MG bar, and it's spanned by the kappa class, and also all the irreducible components of the boundary. Okay. So this is also the philosophy that the belief that the Picard will lies in the tautological cycle, tautological ring. Okay. Okay. Oh, okay. This is a story for curves. So let's move to the next geometric object. I will go to the high dimensional case for the K3 surface. So in high dimensional, the K3 probably is the the easiest example, yeah, for people's understanding. Okay, let me just briefly recall the definition. So the compact complex surface is a K3 if it's simply connected, and there is a nowhere degenerate two form spanned H20. Okay. And we can consider the quasi-polarized K3 of genus G, which is a pair that S is a K3 surface and L will be a NF line bundle, and its self-intersection is 2G minus 2. The reason why we call this genus G, because given such a quasi-polarization, so a general member in the linear system of L is a smooth curve of genus G. So that's kind of a reason why we call this genus G. Okay. Sometimes people also call this is a quasi-polarized K3 surface of degree D. Well, D equals to 2G minus 2. So D is the intersection number of self-intersection of L. Okay. So once you take such a pair, you have a nice modular space. So we have this here, the FG, which is the cross-modular space of quasi-polarized K3 surface of genus G. All right. So this will be an algebraic space. And by using the global Torelli theorem, we know more about this modular space. So FG is actually a 19-dimensional quasi-projective Shimura variety. Okay. So this isomorphism is induced by the period map. I think this is probably well known to everybody, so I will skip the skip the construction, but just state this this modular space is nothing but some Shimura variety. Yeah. So as it's a Shimura variety, then we can compactify the Shimura variety from arithmetic. So there is a Satake compactification, actually called Bali-Borel compactification of Fg. And here in this talk, I will use Fg bar to know this compactification. Of course, there are many other Toreto compactifications, but and because this one is canonical, and also it will be related to the cycle questions. So so we will put a lot of focus on this compactification. Okay. So once you have this modular space and the compactification, and what we want to start is the cycle theory on this modular space. All right. Here is the story on starting the tautological cycles on Fg. So this is largely motivated from Mumford's work. So remember, by Mumford, Mumford defined so-called kappa classes by taking some cycles on the universal family, and then you push forward to the base, and this give you the kappa classes. And this is purely geometric. And Mumford's philosophy is such geometric cycles will control the essential part of the intersection theory of the modular space. And similarly, for high-dimensional varieties, we believe so. Okay, so here is a construction given by Marian, Opera, and Pandra. So they define so-called kappa classes on families of quasi-porous K3 surfaces. Okay, so imagine we have a family of quasi-porous K3. Okay, this is called pi. And we can define the kappa classes as below, given by this equation. So here, the subscript, the index is from A1 to AK, and in B, they're all integers. Okay. So what they are doing is taking the product of the line bundles on the families, okay, and do the self-intersection and or intersections of all these different line bundles. And also you have to intersect with another canonical cycle, which is the second term class of the tension bundle, relative tension bundle. So here AI basically is the times of the self-intersections of each Li. So Li are line bundle. And T pi is the relative tension bundle. You take the second term class and do the self-intersection B times. Okay. Then you push forward. So then you obtain some cycle class on the base on B. Okay. So this is the construction for arbitrary family. And the idea of Marian, Opera, and Panda is they think we can consider this construction applying to some universal family over Fg. Okay. But the difference between Fg and Mg is we're not just considering the universal family over the entire Fg. We are considering the universal family over some classical geometric loci on Fg, because here where our Fg is parameterizing the K3 surface, which is high-dimensional varieties, and on such parameter space, there are natural loci parameterizing the called higher north latitude loci. Okay, it parameterizes the Pika jumping loci. Okay, the parameterize where the K3 surface, whose Pika group, whose Pika number jumps. Okay, so they restrict your universal family to such loci, and they consider the kappa class of this restricted family. Okay, so this will give you many classes. Okay, you can imagine. So they use this way to define the tautological ring. Okay, so this is called the tautological subring on Fg. Okay, a modular space of K3 surfaces. So here, the higher nosology loci we will explain later, and this is very natural. This is kind of the Hodge loci. Okay, and here is a conjecture by Maria Opera and the Panda. Okay, so in this case, they also have some parallel conjectures. First, they conjecture the generators. So the conjecture the generators of this subring is nothing but the components of the higher nosology loci. Okay. It's easy to say that the components of higher nosology loci lies in this subring. But actually, people have more classes because you can vary from A1 to AK, okay? And these A1, AK are arbitrary integers, and B is also arbitrary. And you can actually have more classes. But here, the general conjecture is, although you have many kappa classes, but there are still some linear combination of the reducible component in the higher nosology loci. The other is the vanishing. So they conjecture that when D is larger than the dimension of Fg, which is 19 minus 2, okay, this is 0. This is the second part of the conjecture. And the last one is one dimensionality. So the conjecture when D equals exactly the dimension minus 2, which is 17, this is one dimensional. Okay. And then you may ask whether there is some nice perfect pairing if this is one dimensional. And actually the answer is no. So that's why they didn't conjecture this ring is Gorenstein, because there are already many counterexamples when G equals 2. So the MOP conjecture only has 3 parts. Yeah. So there's no Gorenstein properties for this subring. All right. Any question? Okay. So I want to mention that for the first statement, the generators, the part of the generators, this actually has been already confirmed by Ying and Panda themselves, and also by Bajihong and myself. But our work is in cohomology, okay, and we're using different method. So the method of Ying and Panda, they're using Gromov-Witten theory, which works for K3 surface. But our work is actually work for Shimura varieties, so it's a little different. Yeah. All right. So this conjecture is the an important motivation, at least for me, to study the cycle theory on Shimura varieties. Okay, and I will explain later. So here is a overview of the current progress. Okay, and people can view this as the motivation of this today's talk. So on the left-hand side, I list the properties of the tautological ring of MG, and on the right-hand side, it is the properties of tautological rings on FG. Okay. So for MG, its pK number is 1, and actually the pK group is isomorphic to Z, and its compactification, the Li-Mumford compactification, is isomorphic to Z to the copy of G over 2 plus 2. Okay, there are those copies of Z. And on MG, it's finally generated and has nice vanishing and one-dimension properties. Okay. But on the other hand, when we consider the K3 case, on FG, it has a very large pK group. It's also isomorphic to several copies of Z, and the number of copies is almost 19G over 24. Okay, plus 1. But the pK group of its compactification, the Belli-Borel compactification, is very small. Okay, So this story is totally opposite to the MG case. So MG has a very small pcar, but its compactification has a large pcar. Well, for FG bar, for FG, it has a large pcar, but its compactification, the Belli-Borel compactification, has a very small pcar. Okay. And I'm sorry, here is a typo. So this is open whether the FG, the tautological ring of FG is finally generated. Okay. And for the vanishing and the one-dimension property, we have some evidence. For example, Peterson has shown that when dimension larger, when the degree or co-dimension larger than the dimension -2, this is 0 modular the homologous equivalence. Okay, so this is 0 in cohomology group, but it's still open whether it's 0 in the Chow. And last year, Canning, Opera, and Panda shows that when G equals 2, this is true. Yeah. So actually, we have this when the co-dimension equals dimension -2, this is one-dimensional. Yeah. That's the evidence for their conjecture. All right. Okay. Okay. And later, I will talk about the generalization of this picture, and I will talk about the motivations, why I want to concentrate on starting the pcar group of Belli-Borel compactifications, and why this is isomorphic to Z. Okay, why is Belli-Borel compactification is very small. Okay, let's go to the general citing. So the general citing is we started the Shimura varieties of orthogonal type. Okay. So here, let M to be an integral lattice signatures to N, and D is the associated Hermitian symmetric domain. And here, gamma is some congruent subgroup, and lying inside the stable orthogonal group of O tilde M. So O tilde M is a stable orthogonal group. Of course, you can consider other orthogonal or congruence groups, but for simplicity, I just restrict ourselves to such a group. Yeah. Okay, and we can consider the connected Shimura variety, which is the arithmetic quotient of D by gamma. Okay, so this is a quasi-projective variety, and that will admit canonical compactification. Okay, so you can write the compactification as a product of some graded ring, and this graded ring on the right hand side is the section ring of the Hodge line bundle on this arithmetic quotient. So lambda is the Hodge line bundle on this one. Basically, the Hodge line bundle is the descent of O-1 on D. So on D, this symmetric space, because it's lying in the projected space, it has a O-1 line bundle, and it will descend to this arithmetic quotient. Yeah. This is the construction. And a very important example, at least for our purpose, is when M equals to this special lattice, is the signature 219 lattice. So it's 2 copies of hyperbolic plus 2 copies of E8 and plus one-dimensional lattice. So it's a self-intersection. The norm is 2 minus 2G. Okay, and the arithmetic group is nothing but the stable orthogonal group, and then this arithmetic quotient is nothing but the modular space of quasi-polarized K3 surfaces of genus G. So roughly speaking, the story on FG is just a special case of such Shimura variety. Okay. And let me mention some geometric properties of such varieties. So because this is an arithmetic quotient, and it's easy to see that it has only quotient singularities, because when you take some neat subgroup Okay, it will be smooth, and so it's a final quotient of some neat covering. So it has only quotient singularities. Once you have only quotient singularities, the cycle theory is nice, and even this Shimura variety can be singular, but still its whole group is simple. So everything is just like because it's Q factorial, it's orbifold. So the total theory is similar to the smooth case. Yeah. But once you compactify this Shimura variety, for example, here you take the Bali-Borel quantification, the cycle theory is pretty bad because it can have very, very bad singularities. It can have canonical singularities. And such singularity will cause trouble for your cycle theory. Okay. For example, you lose the control of the Chow ring. Okay. You will see that this is basically this bad singularity is the main reason why the Bali-Borel compactification have very small Picard group. Okay. So let me go to a little bit more on the theory, on this to the cycle theory on Shimura varieties. So here is just parallel to the K3 case actually. So on such a connected Shimura varieties, there are some natural cycles from arithmetic. So you can consider an arbitrary negative definite subspace, okay? And then when you take an orthogonal complement, you give obtain some subdomain, and then your quotient is stabilizer. So this induces a map from this smaller dimensional Shimura variety to your original Shimura variety, okay? And the image called the natural cycles. Okay, you can take arbitrary negative definite subspace. You will obtain these natural cycles, and you can then you can. So here V is ranking from 1 to the top, okay, to n. So the typical example is when this Shimura variety is Fg, and such natural cycles are nothing but the irreducible component of higher north-left loci. Okay, so that's why I said that the cycle theory on modular space of quasi-powers K3 is can be viewed as a special case of cycle theory on Shimura varieties. So from now on, because I believe audience will be more familiar with the Shimura geometry, so you can totally forget the name of higher north-lefties, such stuff. You just think they're just the Shimura subvarieties. Okay, the image of Shimura subvarieties induced by this map. Okay. And then once you have these natural cycles, and we just use these natural cycles to obtain some tautological ring. Okay. So this tautological subring is just generated by all such natural cycles. And then people can ask, what's the property of these tautological cycles or this tautological ring? For example, what are the generators of this subring, and what are the structures of this subring? And here is a conjectural description. I think I should say this is just a conjecture by, it's not written down, but people believe some of them with conjecture. Okay, here I list the 4 problems. So assume the Shimura variety, I'm sorry, here's a typo. Assume the dimension of the Shimura variety is larger than 3. This is not the tautological ring. So the assumption is the dimension of this variety is larger than 3. Okay, this is definitely a typo. And once you assume that, and we believe that the cycle class map of this tautological ring to its cohomology ring will be injected. And the second one is this ring the too many typos here. This ring is finally generated. Sorry, this is a tautological ring finally generated. And the third one is the vanishing. So we believe that when the codimension is larger than the dimension -2, and this will be 0. And the last one will be the one-dimensional property for this tautological subring. So for the first three, people kind of believe this is true, but for the last one, at least for me, I personally doubt whether this is true. Okay, even I restrict ourselves to the case gamma equals to the stable orthogonal group. Okay, so this is I have to say the last problem is pretty hard in general. Yeah. But this is last problem is also one of the motivations of why I'm interested in study the divisors on the or Cartier divisors on the Bally-Borel computation of our Shimura variety. Let me go to the this case. Okay. I mean, I mentioned that the problem 4, okay, is related to the study of divisors on this Shimura variety, and let just me recall the divisors on such Shimura variety. The typical example on such Shimura variety is the Higner divisors. Okay, so choose some non-negative integer m, a non-negative number, rational number m, and an element in the discriminant group of m. One can define so-called the Higner divisor. As I said, this is just some linear combinations of the natural cycles. Okay. So these natural cycles have the numerical data. The numerical data is satisfied when V controls the self-intersection of V. So V now is one-dimensional subspace. Okay, negative definite subspace. So its norm is equal to -m. And when you consider its image in the discriminant group, it's actually the gamma. Okay, so you just take such negative definite subspace and take the natural cycle associated to such a subspace and sum them together. This gives you the Higner divisor. Okay. And when m and gamma are both 0, you take the Hodge-line bundle minus the Hodge-line bundle. So this is the Higner divisor. And the important result here is when the rank of m is larger or equal than 5, the Picard group is spanned by the irreducible components of such Higner divisors. Okay. So this is our previous work. But because the irreducible components is hard to describe, we can have a better description when m is special. That means when m contains 2 hyperbolic lattice, and the gamma is nothing but the stable orthogonal group, one can show that the Picard group of this Shimura variety is actually spanned by the Higner divisors. Okay. So not just spanned by the irreducible component, but by this nice reducible divisors. And this is pretty important in the study of the divisors of Shimura varieties. If it's not spanned by Higner divisors, people will have trouble to understand the entire Picard group. Yeah. Yeah, I will explain in a minute and why this is important. So if the dimension of the here I forgot Bally-Borel. Okay, if the dimension of the Picard group of the Bally-Borel compactification is larger than 1, the problem 4 so likely have a negative answer. I have to say that. Yeah. So this is why I'm interested in studying the Picard group of the Bally-Borel compactification. Here's the typo. This should be the Belley-Borel compactification, okay, the pKa of the Belley-Borel compactification is larger than 1. So in order to cook up some example or counter example, so the first stage maybe is looking at the pKa group of its Belley-Borel compactification. Of course, the study of the pKa of Belley-Borel compactification has its own in geometric interest. For example, so many modular space are isomorphic to the Belley-Borel compactification of such Shimura variety. So that's one motivation. But for myself, this is another important motivation. Yeah. But unfortunately, at least for FG or for larger class of Shimura varieties, for example, if we sacrifice the following properties, we can show that the pKa group of the Belley-Borel compactification is always one-dimensional. So it's just isomorphic to Z. Okay. So this is a joint work with Huang, Mueller, and Ye. Oh, yeah. So here the condition is M has two hyperbolic lattice, and the rank of M is large enough. So that means that the dimension of the Shimura variety is at least 6. Okay, so at least 6-dimensional. Now, larger than 6-dimensional. Okay. And the third condition is a technical condition is when you tensor with ZP, it will contain 3 hyperbolic. Okay, for all OP. Okay. So this is the theorem. So at least the naive counterexample for one-dimension property fails if you want to use the line bundles on Belley-Borel to cook up the counterexample of one-dimensional Shimura variety. This fails. Yeah. So here are some remarks. Yeah, at least for my purpose is to know when this is always one-dimensional. The pKa group of the Belley-Borel compactification is always one-dimensional. Maybe people can find some counterexamples for smaller gamma or for M special. For example, if it's protein contains 2 hyperbolic of OP, and maybe they're a counterexample. But it's also very difficult to verify that. Yeah. Actually, we find that even we can release our condition a little bit. For example, we don't need M tensor ZP contains 3 hyperbolic in some special case. If M is too elementary, and this condition can be released, actually. Yeah. And then the last part is actually I want to emphasize is the proof actually nothing but heavily use the theory of vector valued module form. So that's why I called my title is Theta series and Shimura varieties, which I haven't mentioned them yet. Yeah. Okay. Let's just briefly recall some notations because I think this is well known to the audience. So here are just quickly review the notations. So we consider the vector valued modular forms. So it's just vector valued native function and satisfy some equations under the actions of Mobius transform. Okay. And if the constant term O0, and we call it Caspar form, and we will look at the space of Caspar form for certain weight and type. Okay. And the typical example, if we look at the rho is a trivial representation, it recovers the scalar valued modular form, and we can have the Eisenstein series, which is a modular form of weight 2k, and the type, which is the trivial representation. Okay. And in this talk, I will focus on special type of modular forms, which is coming from the wave representation. And for such modular forms, a main source to contrast those modular forms is from the Theta series. Okay. Can you wait for a second? I think I need to use the power. Oh, 1 second. Oh. Okay, that's good. All right. This is and this is the Borcher's Theta series. Roughly speaking, given any even lattice, there is a wave representation of the multiplicative cover of the SL2. Okay, so I denote by rho L. And when L is definite, one can, Borcher's has found that the vector value of the Theta series defined by the following. So it's just taking the summation of the q to the power of v squared over 2 and EV. Here V runs out all the dual vectors of L, okay? And here H is a harmonic polynomial of degree D. So once you have this Theta series, okay, and this is, Borcher shows that this is a cusp form and of weight D plus the rank of L over 2, and the type is rho L. So, and then we can take the subspace generated by such a Theta series. Okay, here, as we have some ambiguity here, so we can vary our lattice in the genus of L. Okay, because when you in the genus of the lattice, they have the same discriminant group. Okay, so you will get the modular form or cusp form of the same type. Okay, so they have the same representation because one can see that the wave representation only depends on the discriminant group. Once the discriminant group is the same, and you will obtain the same type. Yeah. So when I verify all the definite lattice in the genus of L, I can obtain some subspace. Okay. So this plays a very important role in our study of the pickup group. So, okay. And similarly, one can define the Ziegler Theta series. This is just mentioned. Okay. So finally, I can explain the relation between the modular forms and the Theta series and of our geometric objects. So with our divisors. The first important result is just we have a better description of the pickup group by using the Borcher's work. So Borcher's has a singular theta lifting, and which enables us to give a very explicit description of the pickup group of our Shimura variety. Okay, it gives as follows. Okay, so let A cusp is the subspace generated by all the cusp form and the special Eisenstein series of weight K. Okay, so there is a very special Eisenstein series and of weight K. So its dimension basically is 1 dimension larger than the space of cusp forms. So this A cusp is 1 dimension larger. And our M now is some even lattice of signature 2n and containing 2 hyperbolic. So this is our setting. And then due to the work of Borcher's, we have a isomorphism, okay, by identify our pickup group to the dual of the almost cusp forms. Okay. Also, the map is given as follows. It is sending every Higgs divisor HM gamma to the coefficient functionals. So for example, this coefficient functionals is like this. So given any Fourier expansion of some almost cusp form, okay. So here, AM prime gamma prime is the Fourier coefficients, and this map to AM gamma, okay. So you just take the coefficients of this Fourier expansion at the place where the power of a Q is M, and the basis is exactly E gamma. Okay. So this plays a very important role in the study. Okay. Okay. Now the question, back to our theorem. Our question becomes: when does an element in the pCar of the Shimura variety can be extended to the boundary? Okay. So because we already know that every element in the pCar is some linear combinations of the Higgs divisor under our assumption. So M1 contains two hyperbolic. Every element is a linear combination of the Higgs divisors. Okay. And the answer is there are local obstructions for extending such Higgs divisors to the boundary. Because inside the Shimura variety, the Higgs divisors are Q-Cartier, so they are Q-line bundles. But once you want to extend your Q-Cartier divisors to the boundary is very singular, and there are natural obstructions. Okay, and these obstructions can be computed as below. So we use the local pCar group to compute these obstructions. Okay. So for any point X on the boundary, the local pCar group is basically defined as below. So it's taking you can shrink the neighborhood of X and consider the pCar of this neighborhood and take the limit. Okay. Of course, when you define this, there will be a restriction map from the pCar group to the local pCar group of the Ballet-Borel compactification. Okay. So if we have some divisor in the pCar, it will be extended to the boundary if the order is image in the order local pCar group is trivial. So this is by definition. And the question is when it can be extended to the boundary point. Okay. For example, if this divisor is lambda, is the Hodge line bundle, okay, we know that it can be extended to boundary for sufficiently large n. And if the gamma is neat, actually, lambda itself can be extended to the Ballet-Borel compactification. This is a result by Kai-Wen Lan. Yeah. So, but for when gamma is not neat, lambda is only a Q-line bundle. So you need to take some multiple of lambda so that it can be extended as a line bundle. Okay. Or otherwise, only a Q-line bundle. It's not integral line bundle. Okay, now let's go to the local obstructions for such extension problem. The key result is obtained by the following. So remember that the boundary component of Ballet-Borel modification is very simple because from the construction, each component actually corresponds to some isotropic planes of M. And then we can discuss the obstruction component by component. Okay. So because each component corresponds to a isotropic plane, and we can fix this plane and consider the obstructions for this specific component. And here is the key ingredient of this computation. So this is due to Brenian and Freytag. So suppose M is a lattice of signature 2n, and it contains two hyperbolic, and we take a isotropic plane J, and take the boundary component corresponds to J, okay? And once you have a linear combination of Huygens divisors, then it's trivial in the Picard group of general point of this boundary component if and only if, okay, this sum of their coefficients is 0, okay? So AM gamma is the linear coefficients of H. So H is the linear combination of Huygens divisors with coefficients AM gamma. And the CM gamma is the Fourier expansion, the coefficients of its Fourier expansion of some theta series. So you can take the Fourier coefficients of the theta series, okay, and do some product. Here is actually a Peterson product, and this will be 0, okay. So the result of Brownian vertex actually has more generality, and here I restrict to a very special case, and it can be written as this form, okay. And one can see that here, the relation holds for all theta series, and here J, perp over J, okay, and can vary in the intergenus of its lattice. And H is vary around all the harmonic polynomials of degree 2, okay. All right. Now this is the observation and the questions. The first observation is as M contains hyperbolic, one can show that when J, the boundary component varies. So when you vary the isotropic plane, and J perp over J actually contains the genus of the negative definite lattice of rank M-2, and whose discriminant group is nothing but M due over M. Okay, so when you vary J, you actually obtain the whole genus of this negative definite lattice of given rank and the discriminant group. This is the first observation. Okay, and using this observation, one can obtain a necessary condition, just in using the criterion by Brownian and vertex. So given some linear combination of Huygens divisors, if it can be extended to the Bally-Borel commodification, the boundary of the Bally-Borel commodification, you must satisfy that this equation. So the right-hand side, okay, the sum of AM gamma times CM gamma is 0. And you just need to note that this is nothing but you view H as a coefficient functionals and map F to their coefficient, the summation of the coefficients. Okay, so this just means this equation holds. And for all the F vary in the subspace of theta series. Okay, so this is the key observation of this statement. And second one is, if there is a linear combination of Huygens divisors is proportional to lambda, then this if and only if is 0 for all the F coming from the cusp forms. Okay. This is because the Picard group can be identified as the coefficients functionals of almost the cusp forms. Okay. So if it maps all the cusp forms to 0, then itself must be the Eisenstein series. Then the Eisenstein series will correspond to the Hodge line bundle. Okay. So this is just a view that the modulus Picard group of the modulus of the Shimura variety as almost cusp forms, and the theta series be viewed as the obstruction space. Okay. So the last question is when the obstruction space, okay, occupy the entire cusp forms. Okay. So this question reduced to the pure question of modular forms. So basically ask the basis of the space of cusp forms, whether they are spanned by theta series. Okay. And the idea is we actually show that this is true, okay? And the proof is just relies on this theta lifting results. So we can define some map from the space of cusp forms to the space of modular forms. Okay, this is what I call psi. And for people who are not familiar with the vector value, the Ziegel series, Eisenstein series, and Eichler-Zakir differential operator, you can ignore this. This is a, if you look at the definition, this is typically theta lifting, okay, map. So you're doing the product with the theta series and doing the integration along one side, and you get some modular forms on the other side. And our main theorem is this theta lifting map is injective, and its image is exactly the space of theta forms. Okay. In other words, we have this equality. So the space of cusp forms is spanned by theta series. So this basically is first proved by Mueller for even rank, and then we deal with the odd case. So let me just sketch the proof quickly because it's kind of out of time. So the image of psi is lying in the space of theta series is follows from the Ziegel-Wei formula. And the interesting part will be the injectivity of this map. Okay. And the idea is to use the vector value, the Hecke operators. So this is parallel to the theory of Hecke operators for the scalar valued case. When for scalar valued, it's well known there is a nice Hecke operator. And for vector valued, we have different more complicated construction, but luckily we have such a operator. Okay, its definition is still using some slash operator and by summation over some cosize representative. Okay, this definition is by extending the actions of multiplied cover to the GL2. Okay. Okay, anyway, we have this vector value, the Hecke operator. And the important thing is its properties. This is due to the work of Brenin and Stan, okay? For such Hecke operator, they are actually self-adjoint and with respect to the Peterson inner product. And the subalgebra generated by the Hecke operators which are prime to the level of the lattice, okay, is commutative. So here n is the level of the lattice of our lattice M. And you can look at all the Hecke operators that are co-prime to this level. This is a commutative algebra. And another property is when alpha and beta are co-prime, then T alpha square composed with T beta square is nothing but T alpha beta square. Okay. Okay. And another fact is our theta lifting map is nothing but the summation of such Hecke operators. So this is a series, the summation series of all the Hecke operators. Okay. At least they differ by some non-zero constant. Okay. This is follows from direct computation. So in other words, if you want to show that the psi is injective, it only need to show that the summation of these Hecke operators is injective. So we need to compute the kernel of these Hecke operators. Okay. Okay, the last page. So is to compute the kernel of this sum of all the high operators. The key thing is the space of classical forms is actually spanned by some simultaneous eigenforms of the high operators when the alpha is co-prime to the level. Okay, so then we can take some non-zero simultaneous eigenforms. Okay, and this will help us to diagonalize our map. Okay, so imagine this is a linear map, and we choose a nice basis, and this helps us to diagonal this matrix. And what we need to show is on the diagonal, every eigenvalue is non-zero. And we can show that the eigenvalue is basically some L function. And the value of this L function is non-zero. So this basically shows that this will be injective when the case alpha is co-prime to the level. And to show that when the alpha is not co-prime to the level, this will be complicated thing. And it's a little bit technical. It has to make use of the isotropic lift of modular forms, and which I will not sketch here. But anyway, this is heavily used the properties of the nice property of the vector value of the high operators and computing the associated L functions and give the injectivity of the theta lifting map. Okay, I'm out of time, and I will stop here. Thank you.